Okay, thank you. Okay, so I'll try to be quicker. And so this is a slightly different talk from the previous two ones. So it's not about complexity classes. So nothing about QMA and QCMA. Okay, it's more about query complexity and Boolean functions. So let me just have all the necessary definitions on the first slide. Okay, so it all deals with polynomials. Okay, polynomials in the sense of polynomials over the Boolean cube. So the Boolean case is well known in a way. So essentially we have a Boolean function f on n Boolean variables. Okay, and we can treat these x's like elements of 0 so 1 not as Boolean values but as real numbers, and just put them inside a real polynomial. Okay, and we say that a polynomial p approximates the function f. Okay, so represents the function f in this case. So if its value is exactly equal to the value of the function, okay, and it's between 0 and 1 on everywhere on the hypercube. Okay, and so this makes sense only on the domain because outside of the domain the value of the function is not defined. Okay, but this constraint here is necessary for all of the hypercube. Okay, and non-Boolean case is similar. Okay, now we have D as a subset of strings over some alphabet Q. Okay, and now so at first glance it's not clear how to go to real in this case, but the idea again we go for Boolean case. So we just consider a large number of variables. So instead of having n variables, as in this case, we have n times q variables, where each variable is just an indicator variable saying that that the xj, say, is equal to some value b. Okay, and again, the idea of the representative polynomial that's equal to the value of the function, okay, on the domain and outside of the domain, so on every valid string, it should be again between 0 and 1. Okay, it has a relation to quantum query complexity in a way that it allows to lower bound quantum query complexity. So we can show it's not too hard that if we have a polynomial of, if we have a quantum query algorithm that does something, then there is, and makes t queries, then there is a polynomial of degree 2t whose value is exactly the acceptance probability of the algorithm. So essentially, if we have an exact algorithm, as is written here, so we have the exact degree, as in this case. If we have a bounded error algorithm, then we have what's called an approximate algorithm that is defined similarly, but in this case, we should be close to f, not exactly representing f. Okay, and so turns out, so how do we get to the next slide? Okay, so now there are known relations between the two for the total function. So we just consider total function, so the domain is equal to the hypercube and also the Boolean. Okay, and it seems like there is a lot of relations here, but I'm slightly cheating or not cheating, I don't know, because the original context was slightly different. I said the polynomial, the degree of the polynomial is a lower bound on the quantum query complexity. So essentially this result that I write here of the relation that quantum query complexity of f is polynomial bound to the degree of f is actually initially was defined as a deterministic query complexity is order of degree of f, and even more precise, or maybe the people were interested in the deterministic complexity being upper bounded by the quantum query complexity to the power of 8. Okay, so there are a number of results for the exact degree. I think the best one is cubed. Okay, and the number of results for the approximate degree, so the best is fourth power. Okay, and so this is what this is stated in the terms of the quantum query complexity, and this is like the original formulation. Okay, and so this is the relations for total functions. There are also separations. So and separations are also polynomial, okay, because the relations are polynomial. So the first one was obtained by Andres in 2003, so exactly 20 years ago, is a superlinear between representing degree and quantum query complexity. So in this case, like having a separation between representing degree, so the exact representing polynomial is better than the approximate, okay, because it's kind of lower bound. So it's if we get for the representing, we automatically get it for the approximate as well. So it's like a feature in this case, not a bad thing. Okay, and so this was improved by Aronson et al. In the cheat sheet paper. So we're getting almost quadratic separation. So first power between approximate degree and quantum complexity, almost quadratic between representing degree and quantum complexity. So this is tight due to the result on the previous slide. Okay, and in case of the representing polynomial and QF, it's not known to be tight. So there is second power and third power relations. Okay, and so the natural question is, so what if we take not the total functions, but what if we take partial functions? Okay, and surprisingly, not much was known. Okay, and it's also a natural problem because the partial functions allow usually for much larger separation. So you can usually prove like exponential separation or even polynomial versus a constant separation for partial functions, whereas for the total functions you have all like polynomial separations. Okay, and so I will not go too much into the proof. So what I want to do maybe first is to go a few slides back, okay, and just try to give one slide on the white paper, on the blackboard, sorry. Okay, and if we, just to give you some flavor, maybe why it's not a trivial task. So we can consider a function f of x, okay, which is essentially the R function. So it's 0 if all the input variables are equal to 0, and if it's 1, if 1 xi is equal to 1, and everything else is 0. So in other words, the having rate is equal to exactly 1. Okay, and okay, it's a partial function. It's not defined otherwise. Okay, so let me have this like as a running example. So at first glance, you might see, okay, one thing I can tell that it's hard to do on a quantum computer. So it requires square root of n queries, quantum queries. Okay, and so it's a well-known result. Okay, what's about the polynomial? So one thing to consider is just the sum of all the variables. Okay, so it's a degree 1 polynomial. Okay, but does it work? Okay, it doesn't work because of this crucial condition here. So it should be bounded between 0 and 1 on every input. So it's not bounded, so it's 2, even up to n. It can have value. Okay, and so it's not representing polynomial. It doesn't give a separation. Another idea, okay, we can try and put it inside a different polynomial so that it is bounded, so it's between 0 and 1 on all values of n. So the problem with this, there is no such polynomial. Essentially, the best known polynomial is kind of Chebyshev. Okay, and it has degree roughly square root of n. Yeah, so we're not getting anything here in this case. So how are we going to proceed from this? From this point is, okay, so we're first obtaining the main result. Okay, so we're actually getting a separation. So there are two flavors of the theorem. So this one is non-Boolean, and the second one is Boolean. Okay, so for the non-Boolean case, so we show that if the size of the alphabet is large enough, but polynomial, there exists a function, okay, whose exact polynomial degree is at most 9, and its quantum complexity is of order at least cube root of n. Okay, and so just by taking each input, okay, in this alphabet and encoding as a bit string in a usual way, not in the indexing way as before. So we get the existing family of functions, partial Boolean functions, with exact polynomial degree, representing polynomial degree, which is logarithmic, and quantum complexity is essentially cube root of n. Okay, so this gives an exponential separation in the Boolean case. So the Boolean case is usually like the usual case, which we will consider n constant versus polynomial in the non-Boolean case. Okay, and so my plan is to just explain how this function looks like, and okay, and to prove the polynomial upper bound, because both of these are rather easy. Okay, so that's the formulation of the problem. Okay, so this is over some alphabet of size q. Okay, and there are 3 n input variables, and I break them down into 3 sets, each of size n. Okay, so 1 to n from 2 to n plus 1 to 2n, or from 2n plus 1 to 3n. Okay, and then I consider n cubed, actually, yes, it should be n cubed equation, sorry. It's each equation is of the form, sorry, xa plus xb and plus xc is equal to some value r, a, b, c. Okay, where a comes from the first set, b comes from the second set, and c comes from the third set. Okay, so this gives n cubed equations. Okay, so the problem is, so it's a promise problem, a partial problem, not a partial function. In the negative case, so the input is such that no equation is satisfied. Okay, so the input are the values of the x, and the r actually specifies the problem, so they are not the part of the input. Okay, and in the positive case, there are exactly n equations that are satisfied. Okay, so there are n cubed equations, and out of them exactly n are satisfied. Okay, and if there are other values, then it's not defined. Okay, so it's a bit like a PCP-ish thing. Okay, but okay, in this case. Okay, and now we're going to the polynomial upper bound. So the first observation, that it's easy to count the number of satisfied equations. Okay, so that's the thing that I care about, whether it's 0 or n. Okay, so it's just k of x is just the sum over all a, b, c, so of the indicator functions that xa plus xb plus xc is equal to what it should be equal to. Okay, and so this is not real the variable IOL, but it's easy to write it as a degree-free polynomial. Okay, I just break down into all possible values of xa and xb, and I know what xc is. Okay, and I just write a sum over all these n's. Okay, so this is a trivial degree-free polynomial. Okay, and I want to use a similar idea as here. Okay, I want to plug it into a different polynomial such that it stays bounded. So it's at 0, it is 0. At n, it has value 1. Okay, and otherwise it's still bounded between 0 and 1. Okay, and I said here it's n cubed equations. Okay, at first thing seems that I'm not getting anything out of this, because it's very similar to this case. So where I have from 0, 1, and then all the way up to n. So, and here I have value 0 that interests me, value n that interests me, and then I have all the way up to n cubed. And if I want to do it inside, that would give me a terrible, actually, degree of n, if I just plug it into a Chebyshev polynomial. So, but let's take a look and go back one slide. Okay, so as I said, there are n cubed equations, but actually only 3 n variables. Okay, and these values of r, a, b, c, we can choose them in the way that we like. Okay, so it may seem that maybe not all of the equations actually can be satisfied simultaneously. Okay, so that's the punchline. Okay, we do not get to the all n cubed satisfied equations simultaneously, so we can find the values of r of this right-hand side, so that at most 4 n equations can be satisfied at one input. Okay, so this makes sense because there are 3 n variables, n cubed equations, so we can make it so that there are at most 4 n satisfied. Okay, and the proof is like very easy probabilistic argument. So if we fix 4 n equations, they can be satisfied. The probability they are satisfied can be satisfied is this thing. Okay, so this is the number of possible assignments to the input variable. So this is the number of possible assignments to the right-hand side. So I divide this by this, I get q to the power of minus n. And then I take union bound over all possible choices of these 4 n equations, which is a binomial coefficient, so it's pretty easy. I get this is equal less than 1. Okay, so there exist right-hand sides such that at most 4 n equations can be satisfied. Okay, and then I can continue with my strategy. Essentially, I plug it into this cubic polynomial. Okay, after scaling. Okay, so this is just third degree Chebyshev polynomial, if you're curious. Okay, and I get the degrees at most 3 because this guy has degree 3, this guy has degree 3. So together they give me 9. Okay, and it has all the possible conditions. First, if none equation is satisfied is 0. If all equations satisfied is 1. Okay, in all other cases, I know that between 0 and 4 n equation. So if we divide by n, I get between 0 and 4. So it's between 0 and 1. So this is exactly representing polynomial. Okay, so that's the main idea of the proof. So it's an easy construction to get a polynomial upper bound. So as I said, okay, I have slides for the lower bound because actually I prepared the slides for an earlier meeting. Okay, so but I will not go through them. Okay, and yeah, so the idea of the lower bound, I just want to say one thing. So how we approach this thing using a slightly different interesting problem, which we call hidden tripartite shift problem. Okay, so this is a restriction of the threshold satisfiability problem that we had previously. But in this case, we have this three-dimensional shift matchings in a way, so that we have each element, so we have 2 shifts S and T. So on each element is somehow it's paired or tripled with an shifted by S in here and shifted by T in C. Okay, and so we have the set of all such possible there are n squared of them tripartite matchings, and the idea and the problem is in the negative case no equation is satisfied, so the negative case is exactly the same as before. And the positive case, I want to be more restrictive. I am not saying that there are n equations satisfied. I said that if we take all satisfied equations, they form such a matching here. Okay, so it's an even more restricted problem. So if I prove a lower bound on this automatically gives me a lower bound on the previous problem. Okay, and so why this problem? Because it's closely related to the problem studied by me and Ansis Rosmanis. Okay, so on the question, why did we study this problem previously? Okay, and I think that's maybe the last thing I want to talk about. Okay, why I was interested in this problem in the first case. Because if we take a two-set version of this problem of the hidden shift, it's a hidden shift. It has close relation to the hidden HSP problem. It's known it can be solved in very many queries. Again, it turns out that, I can go back, that, oh sorry, it's forward, that if you take 3 cases, so 3 sets and consider 2 tripartite matchings, it suddenly becomes, like it's very complex, it becomes polynomial. So that was the original motivation behind this particular problem, but it turns out to be also important and useful in proving this separation. Okay, and another thing that this query lower bound actually is sufficiently easy so that it's not too hard to prove. Actually, I have all the proof on slides. So okay, it just goes through the adversary bound. So that's another technique to prove quantum lower bounds. Essentially deals with such matrices. Okay, I just maybe give the definition. So it's a positive times negative input matrix. So like its labels are inputs. Okay, and so we want to find a matrix such that the norm of this matrix is large, but we can modify, like for each input, the matrix so that its norm becomes small, at most 1. And how we can modify the matrix, we can take all the entries where xj is equal to yj, okay, and we can change them arbitrarily, okay, and it is the same if the value of the xj and yj are different. So if the size of the alphabet is large, so most of the cases actually this holds, and this holds only for a few cases. But nevertheless, you can come up with a matrix that gives the required lower bound. Okay, and so I'll just go through the construction. Okay, deals with these matrices. Okay, and a bit of optimization, and you get the result. Okay, and going back to discussion. Okay, so we have three sets. So we might ask, okay, why we have sets? So the answer is because it's easy to prove this lower bound, and it's easy to modify this lower bound. Okay, in fact, it could have worked for two sets, but not for the shifts, because I said for shifts it has logarithmic query complexity. But if we just consider all matchings, so then it can become like a variant of the collision problem or the set equality problem, for which there is no lower bound. Okay, but the problem is this. Okay, it's hard to prove. Okay, I don't know how to prove it. So originally, like the lower bound for the collision problem and also for the set equality problem, which is like technically this what we getting here, is proven using the polynomial method. Okay, and so the same argument that I showed just shows that this just breaks down if we just go from 0 to arbitrary right-hand sides. So what we need to get this small polynomial degree. So we don't know whether this is true. I would suspect that actually this problem is also hard quantumly. I don't know how to prove it. Okay, and then open problem is, okay, can we get constant separation versus polynomial for Boolean functions? So we have constant versus polynomial for non-Boolean functions, so with large alphabet size. Can we do this the same for Boolean functions? Okay, for Boolean functions, so far we have only logarithmic versus polynomial. Okay, and so that's it. Thank you.
I don't know if you want to get coffee or if you want to talk.
We can talk a little bit. Yeah, actually, if there's snacks, I might grab something.
Oh, okay.
That's what I was talking to. We need to talk to. No. Good job. Oh, because he was asking me the same question. That's all. last week he was asking me, so I was trying to remind him of bringing me. Yeah, because she was there, right? And so he was asking exactly this question. Yes. That's right, yeah. But they get sorry, but they get key funds? That's right, okay, yeah, so I remember it. And then, but now you want to bring it to like sharp. Oh, yeah. Sorry, but here's the nice question. Like oh no, we don't know that. Oh yeah, we don't. So we don't.